post hoc. That's important. Because it's not enough in the analysis of variance game or in Bang & Olufsen you compare 3 TV sets and 4 pictures and then you run up to the boss whatever, what was his name? Mancini, I think they changed the guy again. You run up and say, hooray, the TVs are different. The F-test is significant. And he looks at you a little bit. Yeah, fine. Which one should I choose for my production next month? I don't know, they're different. But which one is the best one, right? Tell me which one is the best. We need to tell the story about what's going on. It's just to make it, sorry for the stupidity here in my, but anyway, we need to tell the story about the actual TV sets. So we need to go back to these means of everything, which basically started it all, and which basically people in 3rd grade elementary school could have and would have computed if they were asked to somehow come up with an answer on which TV set has the best noise level. That is, when you ask people to score the noise, which TV set comes with the lowest noise level. Anyone could have computed the mean of each of the 12 TV sets and picked out the one with the lowest noise level, right? And I don't change this fundamental common sense way of looking at data by all the tools I give you now. That fundamental looking at the means still rules. The only thing I give you today is to be a little bit more intelligent in where do I really know for sure whether some prototype is actually better than the other. That how different should prototypes really be to be really importantly different or significantly different. I have 2 here, one is slightly better than the other, but if I take the uncertainty into account, I cannot really choose between them. Maybe we need some other thoughts about why we should choose one for the other. We shouldn't choose it just because it in this test was slightly better than the other, but definitely this one is way off. I'm sure this has a really poor level, so let's not go for that one. Right? So we need to look at an analysis of variance business. We call that the post hoc analysis. So the F-test is the overall test of whether something is really going on. Is there a signal or not? That can be interesting, but it doesn't really tell the story. So we have to go back to the means, and one way of doing it is to compare products with each other in terms of pairwise confidence intervals or pairwise hypothesis test. Much like the 2-sample t-testing that you were already taught, but with a little twist that makes it technically slightly different from the original 2-sample t-test or confidence interval that you were given. On this slide, we have the confidence interval method. Formally, we compared 2 TV sets with each other by the simple choice, the 2 means and the difference between the 2 means. I have a T quantile. I have something which looks very much like the chapter 3 t-test, or I should say the confidence interval version of the inference. Please note that this number, this is the sigma hat squared, to repeat what I said before with the Kahoot question. The sum of squares for the residuals divided by the degrees of freedom, and then I divide by the number of observations in each group. Now we have a subtlety here that we need to deal with, but it's an important subtlety. No, let's not dwell on that one. The subtlety is the distinction between this point and this word up here. I'm distinguishing between, in the top, where I say a single pre-planned confidence interval. By that I would mean if the Bang & Olufsen people, they compare 12 products, but they already decided, for instance, that product 1 and 2, these are our real prototype competitors. The rest maybe would just be some competition out there, products or other prototypes we just take into the test for other reasons. I really have 2 that I plan to choose between, even though I tested 12. Then I have pre-planned that these are the two I want to compare. Nevertheless, at the end of the day, I want to make this comparison. Between, and there's a bit of ethics and thing in this, between the situation where I compare all 12 products between each other. If I compare K equal 12 products, there are 12 times 11 divided by 2. That's 66 different possible pairs that I could compare. And if I go ahead and choose the one with the largest difference among all those 66 comparisons, to say this is my significant result, and then I report the p-value for the choice, that is, I pick the smallest p-value among all 66 p-values. And if I just report that as my p-value, I was cheating, because it's a selected p-value among 66. So, or for that sake, confidence interval. So we have this Bonferroni idea, and we'll come back to it in the hypothesis test, where it might be more easily explained, that when we do many comparisons, whether hypothesis test or confidence intervals, it doesn't really matter. If I do many of them at the same time, then I should not use the 5% level. I should use the 5 divided by 66% level if I do 66 comparisons. That's called a Bonferroni correction. It's a multiplicity correction that protects us from doing selective stats, you know, and cheating. And there is a difference between comparing the means of two that I chose before I even looked at the data. I want to compare those two and then make a confidence interval for those two. Then start picking for among 66 comparisons, I pick the largest one and I give a confidence interval for that. Of course, I will have more significant or clearer statement on that they are different, because it was chosen as the largest among 66. Of course, that is larger due to the selection of being the largest one. So it's a bit of a subtlety, because people, and this is where ethics in research, for instance, can be, we can rapidly go to a gray area zone, and this is a gray zone area in research, this selectiveness that you do, especially in these days of large data, where you collect and collect and collect and collect, and at the end of the day, if you collect data enough, you'll find something to be significant, right? If you didn't protect yourself, if you didn't take into account the selection mechanisms in what you do, that should be part of your probability way of judging what you do. But at the end of the day, it's easy to say, I look at my data, I'm pretty sure I had the original plan to compare these two. Oh, they're also those with the largest effect. Oh, I'm so lucky. Now I get my paper in Science or Nature. This was, oh, I'm so lucky. I'm so happy. I get so rich. I'll get the Nobel Prize. Someone should then stop you a little bit, right? And hey, you picked one out of a million. So if you divide by a million, maybe it's not so significant. Anyway, that was confidence intervals. It's just pairwise confidence intervals, right? We have the same thing on hypothesis testing. That we can do the hypothesis test, for instance, where we compare two specific means. We could do it by t-test. And now I forgot to emphasize the thing, but then I can do it now. The difference now between this t-test and the pooled t-test of chapter 3, which is almost the same. In chapter 3, we would have SP here instead of MSE, otherwise the same formula. But the difference is that the MSE used for pairwise t-testing and also pairwise hypothesis, pairwise confidence intervals, the slide before, please realize that this is a measure that summarizes variability with information coming from all the groups. So when I compare group 1 and 2, yes, when it comes to the numerator, that's the mean of group 1, the mean of group 2. But when I use my statistical measure of noise, I allow myself to collect information from all the groups. based on the assumption that they all measure the same sigma. That's where we use the assumption of the same sigma all over, part of it. So it's a pooled measure of variability. It makes it more powerful to, so making this assumption makes the analysis more powerful. Of course, we need to think about whether the assumption is valid or not. And then we can do standardized or the usual p-value thing. And again, we distinguish between this subtlety here. Either we do a single pre-planned test, or we go picking, we go investigating, we go screening, looking at everything. Well, if you go look at everything, if that's where you are, fair enough. I mean, that's where people are sometimes. Then you need to be more strict on yourself when you look at data. You need to use not a 5%, but a more critical alpha level. When you do all this, I do 100 tests in this. How many would you expect out of 100 tests anyway? Yeah, you would expect 5 significant. Out of 100, that's the definition of the alpha level, right? So, and there is a computation in the note saying that if you do 100 comparisons or so, then you will see at least one significant one with a really high probability. So you need to correct yourself from being fooled about that. And that there are other methods than the Bonferroni. It's not necessarily the best method, but it's a really nice method to learn, to understand. So please read it, because you can use this in many, many contexts. You can use that as a kind of multiplicity correction in many ways of looking at data, not only ANOVA post hoc. Also in finding genes that match certain traits and things like that. That's the same kind of looking for something with a signal, and we need to correct for that. That was the post hoc analysis, an important part of ANOVA to actually, that's where you tell the story about what's going on, right? That's the post hoc. Wow. Seen this one before. Very good. I'm impressed. I could have brought in a new picture that was slightly more relevant for today. I could have put in a third group, but then I was a bit lazy, and then I thought I'd just recopy in the one from last time because it's the same issue. Related to the post hoc analysis that I just talked about, please remember that there is a difference between confidence intervals for the individual means and then doing statistical comparisons between means. And you all got it basically right. We cannot just use the confidence intervals for the individual means and check whether they overlap. That is not good enough, as this example so nicely shows us. And that's the same thing for multiple groups. So here we are. Good, very good. Good job.